In this example, we'll showcase a way we can approach problems that ask us about dimensions of certain objects. This example asks to find the dimension of the span of the vectors given here. And we've got 5 different 4-component vectors here. I want to find the dimension of the span of these vectors. Now, the first point to make here is that the span of any set of vectors is a subspace. If we're looking at all things of the form C1 V1 plus C2 V2 plus C5 V5 for the case above, I can add 2 of these together. I just combine the constants, and I can multiply by a scalar. It just multiplies all the constants by a scalar. So this works as a subspace. It satisfies those properties. It's good to go on that front. So if I'm looking for the dimension of the span of these vectors, what am I actually looking for? Well, I'm looking for a linearly independent spanning set for the span of these vectors. And I can count how many vectors are there, and that will give me the dimension. So what am I going to do? Well, this is already a spanning set for the vectors, so I want to throw out certain vectors to get me to a point where I get to a linearly independent spanning set. So I need to take these vectors here, these 5 that are here, and figure out which of them are linearly independent and use that to get the dimension. We saw problems like this before. What I want to do is put all these into a matrix with these vectors as columns, and then I want to row reduce and figure out where my pivot columns are, because those will give me the linearly independent vectors that I'm looking for. So put this into a matrix as columns. We're going to row reduce and find the pivot columns, because those will give us vectors we can use as this linearly independent set, which will give us our dimension. So let's start putting this into a matrix and see where that takes us. So there is our starting matrix, and now we're going to row reduce from here. So we already have a 1 in the top left corner. We can leave that where it is, and then I can cancel down from there. So my first step here is going to be row 2 is row 2 minus 3, row 1 to get rid of that 3. Row 3 is row 3 minus 2, row 1. And row 4 is row 4 minus 3, row 1 again. So if I do that, the top row stays the same. The next row I get 3 minus 3 is 0. 0 minus 6 is negative 6. 4 plus 3 is 7. Negative 3 minus 15 is minus 18. And negative 4 minus 9 is minus 13. Next row. 2 minus 2 is 0. 1 minus 4 is minus 3. 1.5 plus 2 is 3.5. 1 minus 10 is negative 9. And negative 1/2 minus 6 is negative 6.5. We do the same for the bottom row. And now if you look at this, you might see that some things look like they are repeated and very similar, and in fact they are. I can even see this a little more explicitly if I multiply the third row by 2, which I am allowed to do. And we see that the bottom 3 rows here are identical, which means my next step could be to divide the second row by minus 6, or I can just leave it the way it is. Remember, all I'm looking for here is where are the pivot columns. I don't need to get this into row echelon form. I'm looking for where are the pivot columns. So if I want to not divide the row by minus 6 to bring fractions everywhere, that's fine as long as I can get it to a point where I can see where the pivot columns will be. So my next step can be something like row 3 is row 3 minus row 2, and row 4 is row 4 minus row 2 to give me the following matrix. And now we can see that my pivot columns are going to be this 1 here, and if I were to divide by minus 6, this would be a 1 here. So I have 2 pivot columns, which means I have 2 linearly independent vectors, which means the dimension of this span is 2, which is what the problem wanted us to find. Now for this particular setup, we could say a little bit more. If we scroll back up to the top, we use these vectors in this order to write our matrix, and we saw that our pivot columns were columns 1 and 2. What that means is that I can take these 2 vectors as a basis for the span of all these vectors here. Now the basis is not unique. if you had rearranged your columns to put something else in that second spot, it could probably take the place. But what you'll get every time is you will always get 2 pivot columns, and so a dimension 2 span for this set of vectors here. That's an example showing how you can use techniques we discussed previously, like row reduction, to talk about these new terms like dimension and compute what that is for a given set of vectors.